So, good evening, and let us start today's asset colloquium, which is going to be given by our own Ms. Bhagyashree Chalke from Department of Condensed Matter Physics and Material Science. I feel privileged and also quite happy that I could kind of make her speak. She was a very reluctant colloquium speaker. Every time I talk to her, she used to say very modestly and very humbly, no, not so much, and so on and so forth. So it's always, of course, part of my daily duty to kind of make very reluctant speakers to come and give excellent colloquiums. And I have no doubt about that is going to happen today. And as we all know, of course, she is a real expert on microscopes, electron microscopes. I think she has been on this for more than 20 years, I think to be precise, 22 years. She joined TIFR, see this DERE, right? It was always something we used to look with to many of the Department of High Energy Physics or super seniors. When they come with this degree, then nobody can beat them, because they really know the most basic fundamentals in electronics. And she's from there, I think Xavier Technical Institute, and then she joined TIFR. And since then, generations of telescopes, maybe 5 or 6 generations of telescope, she has really starting from installation, commissioning, maintaining, running. And obviously, I mean, we say quite often we say in the domain of high energy physics, I can't generalize easily, but I think it must be true. The quality of papers depending on quality of data. The quality of data depends on quality of instrument, and the quality of instrument depends on who designs and how they maintain it. So it's in some sense very directly linked, and she really belongs to that kind of genre of people who has a real not only expert but also has a nice connection, nice understanding of the material science that she is actually probing at. So therefore, it is the best of both. So I'm sure we are all looking for very interesting and informative talk from Bhagyashree. Over to you.
Thank you, Satyanarayan, for giving me an opportunity to present a talk here. Good afternoon, everyone. So today I'll be taking you all to a tour of electron microscopy labs of DCMP&MS. We have 4 electron microscopes in all. They need chillers, compressors, UPSs to run smoothly. Again, we have a lot of sample preparation equipment such as grinding units, disc polishers, iron milling units, and iron milling systems. So it's not possible to run such a huge facility alone. I'm fortunate to have a good team with me. Rudhir works on all the microscopes along with me. He works on both the ACMs and also Technite EM and a probe corrected Titan. He has a very good hands in servicing the instruments. So till the company service engineer arrives, he takes care of most of the breakdowns in the instrument. Jayesh is an expert in sample preparation. So TEM sample preparation is a very elongated process, but he does it very nicely. He also works on SEM and Technite EM. Manish has recently joined the group and started working on SEMs. So I'll be introducing you all to SEM, scanning electron microscope, and transmission electron microscope, and give you some examples of the samples studied in SEM and TEM. I'll talk about TEM sample preparation methods. This slide is very primitive for this audience, but since I'm going to talk about microscopes, I thought I'll keep it. Objects like ant and butterfly scales can be seen with naked eye. Milk bacteria, which is about 1 micron in size, needs optical microscope to be seen. Influenza virus is about 100 nanometer in size and can be viewed using SEM. SEM is scanning electron microscope. Atoms which are as small as 100 picometers or lesser than that needs TM, transmission electron microscope, to be seen. Now, I'll give you a real life example of how small the nanometer is. So this is an electron microscopy image of human hair, which is about 100 micron in diameter. So if we cut this hair in the section in the 100 equal sections lengthwise, then one small section is 1 micron, and this 1 micron, if we further divide lengthwise into 1000 equal sections, then one small section is 1 nanometer. So this is the region in which we work, and these are the tools which can see these small objects. Now, what is the resolution? The resolution is the minimum distance which the microscope can detect between the two particles. It is given by this formula. So by looking at the formula, we can clearly say that the resolution is directly proportional to the wavelength of incident radiation, which is used for imaging. So in case of optical microscope, if we use green light, the wavelength is 550 nanometers, then the resolution will be around 300 nanometers. That means we can see objects of 300 nanometers using optical microscope. If you use electron as a source of radiation and accelerate them at 200 keV, then the wavelength is 0.003 nanometer. That means we can view the objects of roughly around 0.0015 nanometer using electron microscopes. Basically, there are two types of electron microscopes, scanning electron microscope and transmission electron microscope. We can see shape, size, and morphology of the object using SEM. If we have EDS, energy dispersive spectrometer attached to it, we can find the elements present in the sample and also detect the chemical composition of the sample. If we have electron beam lithography system attached to the SEM, we can make nano devices using SEM. If we have heating, cooling, biasing holders, we can do some in situ experiments to study real-time dynamics in the sample. SEM needs conducting samples, and if the sample is not conducting, then some conductive layer of carbon or gold is needed. Transmission electron microscopy also, microscope can show you shapes and size of the sample. But here, since the image is formed by the electron beam which is passing through the sample, it cannot show you surface morphology. So SEM gives you 3D kind of image, which gives you a surface morphology, which TEM cannot give. If we have EDS attached to TEM, we can get the chemical composition of the sample. If we have ELS, electron energy loss spectroscope, attached to the TEM, we can get information about oxidation states, dielectric constant, band gap from the sample. TEMs are majorly used to study the crystallography of the sample. We can study the defects in the sample using TEM, and all this information we can get at atomic levels. Here also, if we have heating, cooling holders, we can do some in situ experiments which can tell us, which can give us real-time dynamic of the sample. The most stringent required for TEM is the sample. The TEM sample must be electron transparent. That is, the thickness of the sample should be less than 100 nanometers. Here also, the sample should be conducting. If it is not, then some conductive coating is needed on the sample. These are the 4 microscopes we have. This is Zeiss Evo LS10 SEM. This is a little low resolution microscope, but this microscope can work at higher pressure. So weight samples and biological samples can be using this SEM. This is Zeiss Ultra Plus Field Emission SEM, which is a high resolution SEM. This is TechNite 200 kV transmission electron microscope, and this is a 300 kV probe corrected Titan TEM. Now, what governs the resolution of electron microscope? The electron microscopes have these guns which emit the beam of electrons. So there are 3 types of guns basically: a tungsten, LAB6, that is lanthanum hexaboride crystal, and field emission gun. So here, if you look at this highlighted region, here we can see that the crossover size in case of tungsten filament is in microns, and that in case of field emission gun is 15 nanometers. By crossover, I mean the first beam spot it forms after the electron beam has left the gun. So this itself tells us that the field emission guns have the highest resolution. Second thing to be noted is the brightness. The brightness decides the current in the beam. So here also we can see that tungsten has the brightness of the order of 10 to the power 10, and Schottky field emission gun have brightness of the order of 10 to the power 12. So this is very important when we are using microscope as an analytical tool. So by looking at this, we can say that field emission gun gives the better resolution or the best resolution. Our EVO LS10 SEM has tungsten filament. Technite 200 kV TEM has a lab6 filament, and HR SEM and Titan, they have this Schottky field emission gun. Now, how is image formed using SEM? So when this electron beam falls on the sample, different kinds of signals are emitted from the sample, which are secondary electrons, backscattered electrons, characteristics X-rays. If we analyze these signals properly, then we can get a lot of information about the sample. Secondary electrons are low energy electrons, which gives us information about the sample topography and morphology. Backscattered electrons comes within the sample, and they give us information about the elemental contrast, that is Z contrast in the sample. So they are used for Z contrast imaging. Characteristic X-rays, as the name suggests, are unique to the element present in the sample. So we can detect the elements present in the sample using, if we analyze the energy of this X-ray, and hence we can find the composition. Now, this interaction volume depends on the kV which is used for accelerating the sample, and it is roughly 0.5 micron to 2 micron in case of SEM. This also depends on the Z number of the sample. Now, going to scanning electron microscope. This is the FESEM, field emission SEM. It has a field emission gun. So this is a high resolution microscope, and we can resolve 1 nanometer at 30 kV. This machine has Edx, Oxford Edx as a detector. And this also has a charge compensation system. Now, why charge compensation system needed? Earlier, I mentioned that we need conducting samples to be imaged with SEM. So what happens is when this electron beam hits the sample, the secondary electrons which are emitted from the samples, if they're not grounded properly, it creates electron cloud over the sample. And that electron cloud deflects the primary beam, resulting into the movement of the image, or some portions of the image getting dark, or some portions of the image getting bright excessively. So we can get rid of that by flowing gas, nitrogen gas, locally using small needles. That gas ionizes that electron cloud, and hence we can get images which are distortion free. So this effect is known as charging effect, and we can get rid of that using this charge compensation system. I will not go into the details of instrumentation but rather than focus on the experiments done using these instruments. But here is a cross section of the SEM column. So this is the electron gun, which can be tungsten or PEG anything. It is accelerated downwards by these anodes. Then it has electromagnetic lenses. The first lens is condenser lens. It focuses the beam into a fine spot. This lens also decides the current in the beam. Then there are apertures which eliminates the off-axis electrons, and again there are scan coils because we need to scan the sample, and objective lens is a final probe-forming region. Then these are the various detectors used for detecting different signals. This whole assembly is kept in a vacuum, where the gun is of the order of 10 to the power minus 9 millibar, and sample is at the order of 10 to the power minus 6 millibar. Everard Thornley is the detector used for imaging secondary electrons. The secondary electrons which are emitted from the sample, they are picked by, this is a scintillator photomultiplier kind of detector, which is picked by the scintillator, which converts the electrons into photons, which are guided through this light pipe, and photomultiplier tube multiplies those, and hence we can detect the signal. Now, how is image constructed in SEM? As I mentioned, there are scan coils. So they move the electron beam in X and Y direction on the sample in the raster fashion. And the information collected from this is synchronized with the display and put on the display in point by point mode. Now, how are the grayscales created in the sample? So if the sample has topography, that means it is rough and it has some hilly kind of regions, it has some valley kind of regions. The secondary electrons reaching from these hilly kind of regions, there will be more secondary electrons reaching the detector from these kind of regions. So these will look bright in the image. And the less number of secondary electrons can reach from these valley kind of regions. So these regions will look dark in the image. So that is how the grayscale is created in SEM. Now, here are few examples of images taken using FESM. So in all these cases, the samples have been synthesized by the students here, and the other measurements have been done by the students other than microscopy. So this is an image of copper thin film deposited by magnetron sputtering. Here we can see that the grain size is about 15 to 20 nanometers. So in this thin films, we check for the grain size, we check for the homogeneity of the grains, then we check for the phase of the phase. We detect the elements present in the film, and also if there are any impurities present in that. If we mount the sample cross section in a cross section mode, we can find the thickness of the sample also. Here is an example of graphene drums. So this is the silicon wafer, and these are 1 micron holes made in the silicon wafer using electron beam lithography system in our clean room, and a thin sheet of graphene is laid on that. So here there is already an air trapped here, and when this whole sample goes into the SEM, it faces the high vacuum there. That's why this graphene bulges out. So this is the test to make sure that the graphene sheet which we have laid on the sample is intact. There are no pinholes in the graphene, and there is, there are no, the graphene layer is a continuous one. So this sample was made in Professor Mandar Deshmukh's lab. Here is an example of indium phosphide nanowires grown using MOCVD. So here also we check for the length and diameter of the wire. We check the wire orientation with respect to substrate, and also the composition of wires and the catalyst tip. This is an example of suspended nanowires. So this nanowire, if you look at the dimension, this is very small, about 20 nanometers. So is it possible to measure the electrical properties of such a wire? Yes, if we have a thick wire, we can solder it using a soldering iron and simply measure the electrical properties. But can we make contact to such small wires? Yes, it is possible using electron beam lithography system attached to it. So we have a dedicated electron beam lithography system in our clean room, where you can write patterns as small as 10 nanometers. And we also have a lithography system attached to our EVO SEM, which can write little bigger patterns of 100 to 200 nanometers in size. This is an eye of a fruit fly. As I mentioned earlier, this sample goes into the high vacuum. So for biological samples, it is a little difficult to image the biological samples because they need to retain some moisture in the sample to be imaged. Otherwise, this sample will degrade if we put it into vacuum. But there are some fixation procedures used by biologists by which it creates a certain amount of moisture which is tolerable by the high vacuum, and then we can image these kind of samples also. I mentioned about Z contrast imaging using SEM. So this is such a sample of cerium platinum 4 silicon. Here, by looking at the topography of the sample, we feel that the sample is homogeneous. But when we image the same sample using ASB detector, that is angle selective backscatter detector, we see a very colorful sample. Means the sample is not homogeneous. Here, the bright regions are made up of elements which are high Z or high atomic number, and the gray regions are they are made up of elements which have low atomic numbers. This can be confirmed by doing a point mode EDS analysis on the sample. This is an environmental SEM. It has a tungsten filament, and it's also can go to the pressure of 10 to 3000 Pascal, and hence we can, by using couple of pressure limiting apertures, and hence we can image biological samples or wet samples using this machine. This has a resolution of 5 nanometers at 30 kV. Here are some examples of samples image using ESEM. We all know lotus leaf is hydrophobic in nature, but what makes it hydrophobic? So there are nanostructures on this leaf which make these leaf hydrophobic. So can we, there are efforts being made to modify the surfaces to make them hydrophobic. So can we synthesize similar surface in lab? So yes, so these are the copper nanowires grown in porous anodic alumina template, and after removing template, they form the cluster. And here is an optical image of the water droplet standing on these clustered copper nanowire, which tells us, yes, this sample is hydrophobic in nature. But here, if you look at the droplet size, it is very big. So when we image this sample in EVO mode, we can see the droplets as small as 3 microns to 4 microns also are standing on the sample. That means this sample is truly hydrophobic in nature. Here are some in situ experiments done using the heating and cooling stage in SEM. We have studied alpha tin to beta tin and beta tin to alpha tin transition in SEM. Tin-based alloys will be used as detectors in India-based neutrino observatory. So that's why this work is of important. Alpha tin has diamond cubic structure. It is semiconducting in nature. Beta tin has tetragonal crystal structure. It is metallic in nature. When alpha tin changes to beta tin, it changes volume by 27%. And beta tin to alpha tin transition is a very slow process. This happens at minus 25 degrees centigrade. We kept the sample for 2 days, and then we could see this transformation happening. This is an X-ray diffraction pattern of this sample at room temperature. By indexing the peak, we can clearly see that this is alpha tin. And when the sample was heated to 50 degrees in situ, we could see that the alpha tin has got transferred to beta tin by indexing this XRD line. But can we see this in SEM? Yes, we have made an attempt. So this is an alpha tin sample. So at 35 degrees centigrade, we can see the dimension of the sample. When the sample was heated to 40 degrees centigrade, here we could see the reduction in dimension. That means the alpha tin has transferred to beta tin. As I mentioned earlier, beta to alpha tin transition is very slow. So this sample, this is a beta tin sample. It was kept in SEM for 2 days at minus 25 degrees centigrade. And here, after 2 days, we could see that there are cracks in the sample. That is because the sample has expanded. Energy dispersive spectrometers are used to find elements present in the sample and also the composition of the sample. So when this X-ray photon hits the detector, detector can either be silicon lithium detector or SDT, that is silicon drip detector. It creates a charge pulse which is proportional to the energy of X-ray, and this pulse is processed by the pulse processor and digitized and kept in that particular channel. So this it has a multi-channel analyzer. And these detectors are being outdated now. These are liquid nitrogen cooled detectors. Here, this Silly detector works as a reverse bias spin diode. But we have these detector on our Tech9 and Titan TM. That's why I have included this. These are the new generation detector, which are SDD, silicon drip detector. Here on N-type silicon, there are P-type diffusions made in this concentric ring type fashion. So this geometry helps to give more throughput. That means more number of electron hole pairs are created by the number of photons as compared to this detector. This also works at comparatively higher temperature compared to this, so it doesn't need liquid nitrogen to be cooled with. And the biasing voltage needed for this detector is 4 times lower than this one. EDS has a resolution of 133 eV. Here is an example of Pisco nano ribbons imaged or detected using this EDS technique. So these are nanorobeams which are of 50 nanometers in size and 2 microns in length. By Pisco, I mean bismuth, strontium, calcium, copper oxide. So here the phase of this Pisco material is very important because its TC, superconducting transition, depends on which phase it is in. 2212 Pisco, by 2212 I mean bismuth 2, strontium 2, calcium 1 and copper 2. So 2212 Pisco will have different TC than 2223. Here is the Edx spectrum of the sample, which has energy axis on X here and X-ray counts on Y-axis, and we can see all the peaks. And this is the quantification of this sample, showing that this is 2212 Pisco. As I mentioned earlier, we can get Z contrast images using ASB detector, angle selective backscatter detector. So this is a non-homogeneous sample of bismuth telluride. So here in this bright region, spectrum 2 is from bright region. We can see that it is tellurium rich. Spectrum 3 is little grayish, and we can see that it is bismuth rich because the average Z here is little less as compared to this. Spectrum 4 is from this black region, which clearly shows that there is silicon here, which is even low Z as compared to other materials. We can also take an X-ray map of the sample and calculate the area of the different phases using the image. So this is a SEA image of scandium nickel 2 boron 2 carbon sample, and this also this sample is multi-phase sample. Here also we can see that this gray phase is rich in scandium by looking at scandium K alpha X-ray map, and this bright phase is rich in nickel. So nickel K alpha map shows that this bright region is nickel rich. Going to transmission electron microscopes. So this is the Technite TEM. It has a CCD 1K by 1K CCD for imaging in bright field mode. It has Edx EDS detector for elemental composition, and it has a resolution of 1.4 angstrom. Here is a cross section of TEM. This also has a gun, electron source, and then which is accelerated down by anode. It has condenser lenses to form the fine probe, and it has scan coils where the beam can be moved across the sample. As I mentioned, in case of TEM, the image is formed by the electron beam, which is transmitted through the sample. So here the sample sits here, and below that there are further lenses, projector lenses, to magnify the image. There are different detectors like bright field, annular dark field, high angle annular dark field. So these are the Z contrast or Z contrast detectors in TEM. Here is the Ccd camera, which is used for imaging, and electron energy loss spectroscope sits here. This is the X-ray detector to detect the elements present in the sample. This whole assembly again sits in a high vacuum of where the gun is 10 to the power minus 9 millibar vacuum level, and the sample has 10 to the power minus 6 millibar vacuum level. Now, how is imaging done using TEM? As I mentioned, the electron beam is transmitted through the specimen, and if this direct beam image, then we can get this bright field images. And if we image using the electron beam, which is scattered by the specimen, then we get the dark fields. So in case of TEM, it is very difficult to interpret the contrast. Let's assume you have a sample where you have a carbon grid or carbon film. On that you have metal nanoparticles or gold nanoparticles. Then those gold nanoparticles being thicker will stop the electron beam, and hence those will look little dark in the image. That is called mass thickness contrast. Again, gold being high Z in number will absorb the electrons, hence they will look dark in the sample. If the gold particle is crystalline in nature, it has lattice planes which will diffract the electron beam, and hence it will have a diffraction contrast also. This is the dark field image can give us information about the Z number of the sample, and this is the diffraction pattern which we get from a polycrystalline sample. The diffraction patterns are formed in the backfocal plane of the sample. So if you put an aperture across one particular ring, then it can highlight the crystallites in that particular plane. So this is the information we can get from dark field imaging. In STEM mode, is used in for analytical mode. So here the beam is focused and then moved across the sample, and this is the ray diagram in STEM mode. So here also we have a bright field detector, and because of mass thickness contrast, we can get, so these are the gold particles sitting on a carbon film, carbon grid. So that's why we can see that the gold particles are dark, and carbon, this is the grayish contrast is of carbon grid. And this is the image taken using the dark field detector, which is the Z contrast detector. So here we can see the gold particles as bright and carbon as dark material. Here are some examples of samples image using this TEM. So this is the diffraction pattern of rhenium sulfide single crystal. So we by indexing this diffraction pattern, analyzing this diffraction pattern, we can identify the crystal structure of the sample. This is the lattice image of the sample, high resolution TEM image of the sample, which is formed by which is formed by interference pattern of the diffracted beam and direct beam, and we can find the d-spacings in these particular planes. This is an example of iron oxide nanoparticles, which are 20 nanometers in size, and these are oriented randomly. And if we take a diffraction pattern of this whole region, we can get a ring time dp because diffraction pattern, because there is no particular orientation. This is an image of MOG thin film, which is amorphous in nature. So amorphous samples will show diffraction patterns which are little diffused. Here are some examples image using TEM. As I mentioned, TEM is an excellent tool. In case of TEM, the image is formed by transmitted beam. That is why TEM is an excellent tool to investigate core shell structure. So these are such silver zinc oxide core shell nanowires, where we can see the center portion is silver, and which is of 50 nanometers thick, and it has a thin layer of zinc oxide coating in that. This is an example of indium arsenide nanowire. So this is the low mag image of indium arsenide nanowire, and here we can see some gray and darks contrast here. When we magnify this portion, this is the bright field lattice image of the same sample. Here we can see that these are nothing but the defects. So these wires had twinned defects which were periodic in nature. So this sample is a very good example of defect engineering, because here, after measuring the thermal conductivity of these nanowires, you could found that the thermal conductivity of these defective nanowires was 1,000 times less than the bulk indium arsenide nanowire. Yes. Sorry. As I mentioned, it gives you the Z contrast and diffraction contrast. Here, this silver nanowire, silver being high Z, it has a higher atomic number. That's why we can see that the center portion is silver. And of course, we can do EDS line scans, or we can check this, confirm this thing using elemental analysis also. Zinc oxide being a low Z material, we see little gray lighter contrast in zinc oxide. Now, here is an example of Pisco flake image is in TEM. So this is the TEM SEM image of the Pisco nano ribbons. Here we can, by looking at the high resolution TEM image, we can see that this is a defect-free crystal. This is the diffraction pattern of the same crystal. And by indexing the diffraction pattern, we could find that it has a crystal orthorhombic crystal structure with the lattice parameters mentioned here. This Pisco has a structure where there are copper oxide planes periodically in placed periodically in the crystal. So that is why we get the modulations in this image. And when these modulations are also reflected in diffraction pattern as satellite peaks, which are seen as faint diffraction spots here. This is an image of, this is an example of imaging gallium nitride nanowires. Semiconductor nanowires are very important in applications such as electronics and photonics. This is a SEM image of gallium nitride nanowires. So we have grown these nanowires on different planes of sapphires and studied them. So when we check the nanowires, we check the crystallinity of the wires. Looking at the high resolution TEM image, we can see that these wires are defect free. We check the composition of the tip, we check the composition of the wires, and also another important is the checking the growth direction of the wire. So by indexing the diffraction pattern, we can confirm that the wires grown on C-plane sapphire grew in 10/10 direction, and these are the wires grown on M-plane sapphire, which were, I mean, after analyzing the diffraction patterns, we could find that they were grown in 10/11 direction. So checking the growth direction is little tedious because we have to make sure that the crystal is oriented properly with respect to the zone axis. And then we have to collect two diffraction patterns in the same zone axis plane, on some different plane of the same zone axis. And we have to do this on several nanowires to confirm the growth direction of the nanowire. This will answer your question a little bit. So this is a core shell indium phosphide, indium arsenide nanowire, where indium arsenide is the shell and indium phosphide is a core. So this is the EDS line scan taken across this line, nanowire, and here we can see that arsen is peaking at the edges because of the thickness. That means the shell is made up of indium arsenide and core is made up of indium phosphide. Now here is an example of in situ experiments done in Technite 20 TEM. We have studied hexagonal to cubic transition in silver nanowires. Silver exists in three different polymorphs: cubic 3C, and a hexagonal structure which is 4H and 2H with these lattice parameters. Its density also varies like this. These porous silver nanowires were synthesized in porous anodic alumina template, and after dissolving that template, we could get free silver nanowires. And this is the low MAC TEM image of the sample, and high MAC TEM image shows that these wires are nicely crystalline and defect-free nanowires. Now the question here we asked was, does the 4H to 3C transition depend on a nanowire size? So this is the in situ XRD done on two different diameters of 4H silver nanowire. So this is the data of 200 nanometer diameter wires. So here we can see that at 200, this is the peak corresponding to a 3C phase, and this is the peak corresponding to a 4H phase. So this is the peak corresponding to 4H phase, and this is the peak corresponding to 3C phase. So from this XRD data, we can see that at 200 degrees centigrade itself, some wires have started changing to 3C. And as we go on heating the sample, we can say that by 800 degrees centigrade, most of the wires have already converted to 3C phase. So 200 nanometers wires are not stable. Same experiment when we did with 37 nanometer 4H silver wires. So this is the XRD data of the sample. Here we can see that at 200 degrees centigrade, there is no 3C phase, and at 800 degrees centigrade also, we can see a little amount of 3C phase present in the sample. Now seeing is believing. Can we see this in SEM? So these 4H silver nanowires have a typical bamboo-like surface morphology, which can be clearly seen in this image. When this nanowire sample was heated, we could see that this bamboo-like morphology disappears, and we can see these flat images of the wire. These were heated in the alumina template itself. We have done the same experiment in Technite TEM. So this is the template on which this is a nanowire surface, and here at room temperature we can see this bamboo-like structure very clearly. So this sample was prepared very carefully because we didn't want the sample to get transformed to 4H phase, 3C phase while preparing the sample. So the milling was done at low temperature. This is the diffraction pattern of the wire at room temperature, which tells that this wire is 4H in phase. When we heated this sample in TEM at 800 degrees centigrade, we could see that this bombuloid morphology has disappeared completely and the sample has transferred to a 3C material. So this diffraction pattern, when it was indexed, it was found to be 111 phase of 111 plane of 3C. So by this experiment, we can conclude that metastable phases such as 4S silver nanowires can be stabilized if we use a proper thermally stable cage around it, and if we can reduce the size of the nanowires or size of the sample. This is the second phase transformation which we studied in Technite TM. So this is amorphous polycrystalline thin film made by pulse laser deposition. The high resolution TEM image shows that this is a polycrystalline thin film, and this is the diffraction pattern of the same taken at 100 degrees centigrade. So we can see that till 300 degrees centigrade, the diffraction patterns are diffuse. That means the film is still amorphous. And when it was heated to 400 degrees centigrade, we could see a polycrystalline ring kind of diffraction pattern, which showed that the film has turned into a polycrystalline sample. As I mentioned earlier, TM sample preparation is very tedious job. Here, the job is to make sample electron transparent and thickness should be less than 100 nanometer. So if we have a powder sample, we can simply sonicate it in suitable solvent and then put a drop on a carbon grid. If we have a bulk metallic sample, it can be used by, it can be prepared by using this etching with electrolyte. So there is an electrolyte bath, so suitable electrolyte is selected, and there are fine nozzles. The sample first is thinned down to 100 micron, and it is mounted vertically in this bath, and electrolyte is spread by these nozzles, which makes the sample electron transparent. Other samples can be made by using these steps. So here we cut the 3 mm sample disc from the sample and then we grind the sample to 100 micron thickness. Then using a dimple grinder, we make a dimple in the sample. Then the sample left is around 20 micron. Then by using focused this argon ion milling, we create perforation in the sample, which are electron transparent. And if we have a thin film and if you want to image the cross section of the sample, then we cut the films into 0.7 by 1 mm. We make a sandwich of them, and that sandwich is put into the titanium slot grid. And this titanium slot grid is processed in this route again to get a final TM sample. TM sample preparation is a very tedious job, and you can imagine at every stage we have to handle a sample which is 100 micron thick. So this really needs a skill, and sample preparation can take as long as 3 to 4 days because the ion milling times depend on the sample, and they can be as long as 6 hours to 8 hours. So Jayesh does that job very sincerely for us. That's why we can get very good TM samples. I'll come to aberration corrected electron microscope, Titan. Now, why do we need probe corrector? If you remember, I mentioned you that if we use 200 kV electron beam, we should get a resolution of 0.0015 nanometer. But do we get that? No, because the electromagnetic lenses are not perfect. And instead of forming a spot, they form a disk. That's why we are not able to image to that resolution. But then what is the solution to that? We can create the solution to that is we can add probe corrector optics in the column, which are couple of lenses more, which try to focus the beam to a point mode, much finer beam. So we have a Titan machine which has this probe corrector. So this is the Titan TEM, which has 2K by 2K Ccd for bright field imaging. It has high angle annular detector for STEM imaging, and it has a probe corrector. That's why its resolution is 0.7 angstrom, and it also has EDS for elemental detection. It has electron energy loss spectroscope for detecting elements present in the sample. Basically, yields are used for detecting low G elements, which cannot be done very efficiently using EDS. So this is the yields spectrometer. When the electron beam passes through the sample, it loses some amount of energy. And if we can measure that energy loss, then we can identify the elements present in the sample. For example, if you have a sample and you find electron beam exiting the sample with energy less, energy difference of 285 eV, then we can make sure we can be confident that there is a carbon present in the sample, because that is the 285 eV is the energy needed for inertial ionization of the carbon. The yield spectrometer is nothing but the electron beam is passed through this aperture and it is bent by it is bent by a magnetic field, and there is a magnetic prism here which is similar to glass prism. Here the glass prism disperses light, here the magnetic prism disperses the electrons, and a spectrum is formed in the dispersion plane, where x-axis is energy and y-axis is the counts of electrons which have lost the energy at that particular EV. This is the typical yield spectrum, which contains zero loss peak, which is formed by the direct beam. Then it has plasmon peaks, which mostly arises because of the thickness of the sample. Then it has a low loss peaks, which give us information about band gaps and oxidation state, dielectric constant, etc. from the sample. And this is the core loss peak region, which can give us information about elements present in the sample. So this is the typical spectra of different aluminum compounds. So by looking at this spectra, we can see aluminum nitride peak has a different position. So by looking at the peak position, we can identify this is aluminum nitride. Sapphire has a different peak shape. So by looking at the peak shape itself, we can identify that this is sapphire in the sample. Now here are examples of samples imaged using TEM. So these are the KCC or fibrous silica samples prepared in Professor Vivek Polshettiwar's lab, and they were loaded with platinum particles. So these bright spots which you see, they are platinum particles, and when we magnified these bright spots, or when we magnified the region here, we could see fine bright spots. These are pseudo platinum single atoms. If you look at the scale bar, this much is 5 nanometers. That means that every small bright spot which you see is 100 picometers in size. So this kind of imaging cannot be done using any other microscope. So this kind of imaging needs probe corrector microscope if you want to image at this scale or this level. This is again an example of tantalum thin film prepared by magnetron sputtering. Here the different size of crystallites were prepared. So this is the smallest crystallite, which is about 2 nanometers, prepared by using magnetron sputtering. So this is a single gray or single crystal of the alpha tantalum. And here the question they addressed was, is there any lower limit to the crystallite size on superconductivity? So this was a very crucial image for this kind of work. As I mentioned earlier, from TEM, we can get information at atomic scale. So this is the strontium titanate single crystal. So here we can see the bright atoms. So these are single atom columns. The bright atoms are strontium and the gray atoms are titanium. So line scan along the blue arrow shows the spacing between strontium atom, which is 0.3 nanometers, and the line scan along the this red line shows the spacing between strontium and titanium atom, which was about 0.28 nanometer. So this image is from a standard strontium titanate sample. This was taken here. It was taken by Dr. Purandareji. Now, here is an example of gallium nitride nanowire studied using TEM. So this is a SEM image of gallium nitride nanowire. Here we try to answer the question whether this nickel-assisted growth of gallium nitride happens via VLS mode or VSS. By VLS, I mean vapor liquid solid, and by VSS, I mean vapor solid state mechanism. So we did Edx on the tips of 60 such nanowires, and then we could find that the tip composition was Ga2Ni3. When we did Ilse line scan across the tip, the catalytic tip, we could find that this tip was a single crystalline, and again Ilse data also confirmed that it is Ni2Ga3. When we did high resolution imaging of the tip, we could see that it has a crystal structure of hexagonal with these lattice parameters. So this also matched with Ni2Ga3 tip. It confirmed that the tip is Ni2Ga3. And when we looked at the phase diagram of nickel gallium, we could find that Ni2Ga3 cannot be in liquid, cannot be in solid form. Solid form at the growth temperature of the wires. That means this growth has happened via VSS mechanism, that is vapor solid mechanism. Here is an example of DC sputtered tungsten thin films. So these films are very thin, about 20 to 30 nanometers in size. So it is difficult to get crystallography information from these films. Because if it has small inclusions of 5 nanometers or 2 nanometer crystallites, then definitely X-ray is not going to pick it up. This is a high resolution TEM showing the dark contrast in the center, which is a crystal about 5 nanometers thick. And here is which will be seen as bright speck in STM image. When we take the diffraction pattern from this spot, we can see that it has nice spots. That means this particular bright contrast is a crystallite material. When we collected a diffraction pattern from the gray region, it matched to a amorphous region. So that means we can study the inclusions, crystallite inclusions in DC sputtered tungsten thin films. Now, here is an example of Ws2 Nano Tubes. These were prepared by sulfurization of tungsten thin films, which were prepared by electron beam evaporation. And this is the SEM image where we can see a nanotube here. And by taking the STM image, these are the atomic columns. We can see, we can study the folding mechanism of these these tubes, and by studying the diffraction pattern, we can study we studied the chirality in these tubes. This is little unconventional microscopy. See the samples which has short range order can be characterized by using neutron diffraction or exact technique. The samples having long range order can be characterized by using TEM or X-ray diffraction techniques. But the samples which have medium range order, which is about 0.1 nanometer to 3 nanometers, there is no technique available to study that kind of order. So, bulk metallic glasses are generally studied, generally have MRO, and the hardness of the BMG bulk metallic glass depends on the MRO present in that is medium range order present in that. So here is a technique to evaluate the medium range order in the sample. So since the sample is amorphous, we get a diffraction pattern like this. And if we put a objective aperture across the diffraction pattern, and if we move it radially, we can collect the dark field images. And here we can see this is the dark field image corresponding to this ring, this bright ring, which shows a very nice speckle contrast. And if we calculate the variance of this image, that can tell us about the medium range order in the sample. So here, this is the diffraction pattern from this ring, which is very faint. So there is hardly any contrast here. That's why we don't see any speckle contrast here. Rudhir has worked extensively on this technique. He wrote scripts to evaluate the variance of the sample. And we have studied copper titanium bulk metallic glass using this technique. So this is amorphous copper titanium ribbon sample. It was prepared by melt spinning, and a TEM sample was prepared. The high resolution TEM image shows, bright field high resolution TEM image shows that this sample is amorphous in nature. And this is the variance of the sample plotted with respect to K. Here we could see that at room temperature, the variance is very high. That means it had medium range order. And as we heated the sample, we can see the medium range order disappearing. This work is still in progress. So here I come to the end of the talk. I thank you, Professor Bhushan Ayub, because he brought all these instruments and we could work on those. After his retirement, Professor Arnab Bhattacharya took over as chairman of Electron Microscopy. Now Professor Tamilve is chairman of Electron Microscopy. So they have helped us to run this machine. Dr. Purandre taught us the microscopy techniques. I thank all my DCMP colleagues and other TIFR colleagues also, because to run this machine throughout and to reduce the downtime of the machine, I keep on borrowing many stuff from other labs, right from the O-rings to the dry pumps. So thank you all. Yeah.
Yeah, so as you mentioned, Bhagyashree, it's, I mean, even though the facility is there with you and you are expert, but the users are all throughout the institute, and also I think a
Yes,
lot
outside.
from outside
Yes.
coming in. And so it's not just only for your group or department. So and maintaining and ensuring the quality of data is sometimes quite a thankless job, right? And okay, so questions.
In SEM, there is no limit to sample size. We can put 1 inch, 2 inch sample also. But TM needs 3 mm disk only. That is the sample size. Sorry.
How do you test the sample?
Samples. Basically, we don't allow any powder samples because that is not good for the everything sits in the high vacuum and it's not good for columns. So we don't put powder samples directly. There is a way to prepare powder samples. We drop cast and then pump those samples elsewhere overnight and then load them in the SEM.
Do you test with any electronic equipment by taking the connections from the samples? That type of test you do?
No, we have feed through. So if we have that kind of samples, like we were trying to simulate these graphene drums by giving external voltage. So those things we do try. We have the feed throughs for those kind of measurements in SEM, not in TE.
Can you tell me how to handle the biological samples?
Yeah, biological samples, in fact, they can be viewed directly in environmental SEM at high pressures. But if you want to view them in high vacuum, then they need to be fixed properly. So there are some chemicals. So that chemical treatment is given to those samples. And there are equipments like critical point dryer. So the samples are dried there and then they can be loaded in the high vacuum SEM. And of course, they will need a conductive coating because they are definitely non-conductive.
They're not going to be live in that sense, or will they?
No.
No. So I understand, like, I mean, these going all the way to a fraction of nanometers, tens or maybe hundreds. So is there a kind of a procedure where you kind of do something like a calibration time to time, and that kind of tells you that your instruments are looking at the least counts which are expected? Is there some procedures like that?
Yes, we have standard samples and we have to calibrate the equipments time to time. And for the aberration corrected microscope, we have to align the microscope using those standard specification, and that alignment procedure itself takes quite a long time. Yeah.
How do you calibrate?
In case of aberration corrected microscope, it is like it depends on at what magnification you want to image sample. If you really want to go to that atomic level, then yes, before loading the sample, you need to do that alignment. Other microscopes, those are like we can do, let's say once in 3 months or so. For other microscope, in case of probe corrected microscope, it is just before loading the sample. If you want to image at atomic scale.
Another thing is normally these are of course very extremely expensive, several crores. So how when things don't work well, which you probably realize when you do a sample or maybe during calibration, etc. So how do you proceed to get it corrected?
Basically, we have all the SEMs are in maintenance contract. But if you see, there are only 2 service engineers for whole of the Western region, and they might be handling somewhere around 50 to 70 SEMs. And these are high vacuum systems. So if the engineer is stuck at one place, it can take as long as 3 to 4 days for him to come out from that place. So it's difficult to get service. So most of the things we try to fix it here, and in certain cases, see, nowadays they give just black boxes. We don't have any circuit diagrams, nothing.
Yeah,
so we can't do any further servicing, but we try to do as much as we can here. And then of course the service engineers are there to help.
One technical question. You said that you saw there are imperfection in electrostatic and magnetic lenses. You saw that in simulation, or you can verify?
That is a known thing. The lenses cannot focus the beam at the.
No, do you have any simulation software to calculate ion trajectories, or it is just?
The simulation softwares are available. Yes, we can do all those things there. They are available.
Okay.
We have not calculated, but the simulation softwares are available. That is how the lenses are designed. Na? When they design, they have to do all this simulation, and then only they proceed with it.
So this is something little bit, let us say, a part of your microscopes, namely the sensors. So what are the kind of developments that you see? For example,
a lot. See, many times students come complaining that, oh, I want these kind of images. So but they are looking at the microscope, which is recently bought. Our microscopes are 15 years old. So with a probe corrected microscope also, we have a 2K by 2K CCD. So nowadays you won't find 2K by 2K CCD anywhere. Now the CCDs have improved like anything in last 15 years. So everywhere you will find 4K by 4K CCD, and the dynamic range of the CCD is very high. There are very good quality detectors available. So definitely there is a lot of improvement in the detectors. For example, if you say Edx, like we have 30 mm square LN2 based detector. And nowadays, if you see, there are dual detectors, which are 100 mm square, and that too, they are Peltier cooled. So the throughput is so high. So if we try to map a sample in TEM, whatever job we can do in 1 hour, modern microscope can finish it in 10 minutes. So that is the change in the technology.
If I can ask one more question. So, I mean, do you also do some kind of image enhancing techniques after you collect the raw data from the microscopes? Is there such techniques also become part and parcel of your business?
Yeah, there are a lot of softwares, but basically we hand over raw images to the student, and then it is student's job to do whatever they want with that image.
But they typically, like what you said, I mean, of course, the generations of microscopes, I mean, you can never really, as we are talking, I'm sure the next instrument must be getting designed. Yes. So therefore, but to use the instrument in sufficiently long period, because cost a lot of money. So there could be also these kind of techniques, or, I mean, you have a raw data which gives you certain resolution, let us say, that is collected, but then maybe people can take multiple images, or maybe there's some other, I don't know how.
Of course, that can
and then enhance the.
Yeah, that can be done, but of course there is a limit to it. If the raw data is.
Okay. So any other questions to Bhagyashree? If no other questions, so as per our asset colloquium tradition, let us thank the speakers. Let me see which is up and down. By giving this. Actually, I saw the name.
Oh.
This is, I think, Ms. Rajan Meera.
Yeah. Okay.
Yeah.
So thank you.
Please join for a cup of coffee.
Thank you.